This is Unit 2, Motion in One Dimension, Lesson B, Acceleration. What we're going to do in this lesson is describe the difference between accelerated motion and non-accelerated motion and introduce the kinematic equations for constant acceleration. So at the end of this lesson, you should be able to describe the motion in terms of changing velocity, compare and interpret graphical representations of accelerated and non-accelerated motions, and apply kinematics equations to calculate distance, time, or velocity under conditions of constant acceleration. So as we covered last time, velocity is a change in position. Acceleration, then, is a change in velocity. Okay? Acceleration is the rate at which velocity changes over time. An object accelerates if its speed, direction, or both change. Now, because acceleration has both speed and direction involved with it, it is a vector. Okay? Here is an equation, then, for the definition of acceleration. Okay? It's the changing velocity over time. And so if we look at the units, if we analyze units of this, we would see that we've got meters per second, that's units of velocity, over time, which is seconds, giving us meters per second squared. That will be the units of acceleration, meters per second squared. So let's take a look at this example. We have a shuttle bus slows down to a stop with an average acceleration of negative 1.8 meters per second squared. How long does it take the bus to slow from 9 meters per second to 0 meters per second? This negative 1.8 meters per second squared means that this acceleration is in the direction opposite to the direction of the velocity. So let's look at what this object is doing. Okay. This object is moving along, and I'm using this dot to represent this bus. And as it moves, it's slowing to a stop. If we put in the velocity during each of these time intervals, okay, so each dot represents a time interval, okay, and they're equal time intervals. The green arrows indicate the velocity, and so we see then that this object, that the bus, is slowing to a stop. So in this type of diagram, it's called a motion diagram, and our acceleration will always point in the direction toward the longer velocity arrows. So our acceleration points in this direction. So our velocity is pointing to the right, our acceleration is pointing to the left, gives us a negative acceleration. We start out with a velocity of 9 meters per second. We have a final velocity of 0 meters per second. Our acceleration is this negative 1.8 meters per second squared. We want to find out what our time is. We use our equation for the average acceleration then and substitute in these values. And here we can see when we do that, we have our negative 1.8 here. We have our initial velocity here. So a change in velocity then is the final minus the initial velocity, which we can see is going to give us a negative over here, which will end up giving us a positive time when we divide 9 by 1.8 and get 5 seconds. Okay, so stop for a moment and look at practice B in your packet and do numbers 1 and 2 before continuing. Okay, so acceleration is a vector, so it has both direction and magnitude, so it has a size and a direction. So suppose this car here is speeding up to the right so that it's the displacement and the velocity are positive. So this trip is showing 3 separate sections of motion here. Car speeds up first, it goes at a constant velocity in the middle, and slows to a stop at the end. We're going to look here specifically at the relationship between the velocity direction and the acceleration direction. As it begins to speed up to the right, its speed is increasing in this positive direction. Therefore, its acceleration is going in the positive direction. and both velocity and acceleration are positive. During this middle part of the trip, it travels at a constant velocity. So anytime there's a constant velocity, the velocity is not changing. Therefore, we have to have zero acceleration. At the end here, it slows to a stop. Its velocity continues in the positive direction, but it's slowing to a stop. So therefore, the acceleration points to the left in the negative direction. So we can represent this changing velocity in what's called a velocity time graph. So here we have a graph of velocity over time. This object, let's say it's a train, is starting out from a station and moves throughout its motion. So in the beginning here, as it starts with zero velocity here, it increases its velocity. So during point A, at point A here, this velocity is increasing in the positive direction, and so we have a positive acceleration. During this portion of the trip right here, where this train is now moving with a constant velocity, it has a positive constant velocity because it's a straight line here. Here, the part B then is showing zero acceleration. Here, our train is slowing down to a stop. So through motion C on here, we have a negative acceleration. So here's another velocity time graph of an object here. Starting at zero velocity, it increases its velocity to 60 meters per minute, then travels at a constant velocity here. And then it has this negative, or it has a decreasing velocity, and then it goes into this negative velocity. So let's look at what's happening right here. As this object is moving, it's moving in this positive direction here. It's increasing its speed. It moves at a constant velocity. Then it slows down. At this point right here, its velocity goes to zero. As soon as it dips below this x-axis, then it's moving with a negative velocity, which means it's changed directions. So right at this point right here, this object has changed directions. Okay. So it's moving then, it's increasing its speed. The speed it's going faster and faster in the negative direction. Here, what this is showing is that it's slowing down. It doesn't change directions at this point. At this point right here, it just begins to slow down. It's still moving in the negative direction. So we can more fully describe an object's motion by looking at the signs of velocity and acceleration. They can combine them to give an overall description of an object's motion. This table here then gives us the conditions under which our objects will be speeding up, slowing down, have a constant velocity, speeding up from rest, or if they're staying at rest. So if an object has both positive velocity and acceleration, or both negative velocity and acceleration, our object is speeding up. If the signs are opposite, with positive velocity and negative acceleration, or the opposite there, we're slowing down. And we can look at this another way. So here are four velocity time graphs, along with four motion diagrams showing what this graph is telling us. So in this velocity time graph, our object is speeding up. Okay, velocity is increasing to the right because that's our positive direction. Therefore, we have a positive acceleration. That's what we would expect. Okay, here our object is slowing down. It's moving in the positive direction because on our velocity time graph, the line is above the x-axis. On a velocity time graph, anytime the line is above the x-axis, that is showing us a positive velocity. So we've got positive velocity, but it's slowing down, therefore we have a negative acceleration. These two, the first two pictures here, give us an indication, shows us what we would expect. Object speeds up, positive acceleration, object slows down, negative acceleration. The next two graphs here, these show us a little bit of a counterintuitive example. Okay, here we're moving to the left or down because we're in the negative direction. Okay, so we're moving in a negative direction here. and we're slowing down. We know we're slowing down because our slope, our line on our velocity graph is going towards zero. So we've got to be slowing down, moving to the left, gives us a positive acceleration. Here, we're speeding up, but we're moving in a negative direction. Therefore, we have a negative acceleration. Okay? These graphs are showing us then that the slope of a velocity time graph will give us the acceleration. If that slope is positive, it's a positive acceleration. If that slope is negative, it's a negative acceleration. Okay, so now we're going to move into motions with constant acceleration. Acceleration is changing velocity. Constant acceleration means that the velocity of an object is changing at a constant rate. So something with a constant acceleration of 10 meters per second squared means that for every second that passes, the velocity changes by 10 meters per second. If it starts from rest, after the first second, it's going 10 meters per second. After the second second, it's going 20 meters per second. After the third second, it's going 30 meters per second, and so on. So this picture here shows an object being dropped. Okay, while this thing is moving, its image was captured 10 times in a second. So the time interval between these successive images is 0.1 seconds. Okay, so as this object's velocity increases, it travels a greater distance during each time interval, which we can see. The graph then of this motion indicates a constantly changing velocity. Okay, we end up with this straight sloped line of this constantly changing velocity, telling us then that we have this acceleration. So what we can do is we can take these relationships between displacement, velocity, and constant acceleration and express them in equations that apply to any object that's moving with a constant acceleration. So the first equation, we're going to look at 4 of them, okay, deals with displacement, and displacement depends on acceleration, initial velocity, and time. So we know that when an object is moving with a constant velocity, or we're looking for an average velocity, we can use delta x over t, okay. So for an object moving with constant acceleration, the average velocity is equal to the average of the initial velocity and final velocity. So if we averaged out the initial velocity and final velocity, we could get an average velocity. We can also take the change in position over the amount of time that it takes to change that position and get an average velocity. So we have 2 expressions for average velocity. So if we equate those 2 expressions together, here, what we're saying is the displacement over the time is the same as the initial velocity plus the final velocity divided by 2. So if we put these together and then solve for this displacement, we end up with this equation right here, where we've got our displacement is equal to 1/2 the initial velocity plus the final velocity times the time. So let's look at an example. We have a race car reaches a speed of 42 meters per second and begins to uniform negative acceleration using its parachute and braking system, comes to rest 5.5 seconds later. We want to find how far the car moves while stopping. So we begin looking at this car's motion from where it's going 42 meters per second. It ends at 0 meters per second. It takes 5.5 seconds to get there. We want to know how far it goes. So using this equation right here, we substitute in those values, we get 120 meters. So stop for a moment and look at practice C and do numbers 1 and 2. So now in that previous example, we didn't know anything about the acceleration. We weren't told anything about the acceleration, so we could use that equation. When we have situations where we do know the acceleration or we're asked for the acceleration, there are these other 3 equations that we're going to develop right now. The first one deals with final velocity depending on the initial velocity, acceleration, and time. So remember, our definition for acceleration is this acceleration is changing velocity over time, okay, which is reflected right here in this right here, okay. So if we solve this for the changing velocity, we end up with this right here. We can multiply the time on the over here, and we get AT equals VF minus VI. We can then add VI over here. We end up with this expression here, where VF is equal to VI plus AT. So we rearrange this equation to get this right here, okay? So VF equals VI plus AT. This will be velocity with constant acceleration. We can use this equation to find the final velocity of an object after it's accelerated at a constant rate for any time interval. So if we want to know the displacement of an object moving with constant acceleration over some certain time interval, we can obtain this another useful expression for displacement by substituting the expression for VF into the expression for delta x. So here is the first equation that we developed, and here is the one that we just did, right? When we kind of clean it up a little bit, it looks like this. So we distribute this 1/2 in there, and we end up with this equation right here for displacement with constant acceleration. This is VIT plus 1/2 AT squared. So now we've got these two equations with dealing with acceleration that we can work with. So let's look at an example. We have a plane that starts at rest at one end of a runway, undergoes a uniform acceleration of 4.8 meters per second squared for 15 seconds before taking off. We want to know what is its speed at takeoff, and then how long does the runway have to be for the plane to be able to take off. So here's here's our airplane. Here's the stuff that we know and what we want to find. We're going to first use the equation for the velocity of a constantly accelerated object, which is VF equals VI plus AT. So when we substitute in our values on this, we end up with a final velocity of 72 meters per second. But we also want to know what our displacement is during this time. So for that, we're going to use our displacement equation, which is this, and gives us a displacement of 540 meters. Okay, so stop. There's practice D. Let's do number 2 and 3 before moving on. So now we're going to look at our final constant acceleration equation. Here we have final velocity after any displacement is going to be VF squared equals VI squared plus 2AX. So this is the fourth of our 4 acceleration equations. So let's look at an example using it. So we have a person pushing a stroller starting from rest. The uniform acceleration is a rate of 0.5 meters per second squared. What is the velocity of the stroller after it's traveled 4.75 meters? So let's look at what we're given and what we need to find. We're given our initial velocity, we're given our acceleration, we're given our displacement. We need to know what our final velocity is. If we use this third equation, then we can substitute in our various values. So we start with 0 velocity. We have an acceleration of 0.5, and we go a displacement of 4.75 meters. And putting all that together, we end up with this 4.75. So our final velocity squared is 4.75. We run the square root on that, and we end up with a final velocity of 2.18 meters per second. So these are the 4 possible equations in situations with constant acceleration. These equations presented in this section, it's possible to solve any problem involving one-dimensional motion with uniform acceleration. So what I've done here is I've created this table for you to use to eliminate equations you can't use in a given problem situation. So when you're given a problem, we want to it's a constant acceleration problem. We know that we can use one of these four equations to help us solve that problem or a part of that problem. So when we write down the given information, right, and we write down the information that we're looking to find, it's going to tell us what we have and what we don't have, okay? So then we can turn to the table to figure out which equations to use. So these three equations all involve acceleration. So if we're in a situation where you are not told anything about the acceleration and you're not asked to find the acceleration, you can use this equation, right? If you're given three of these variables, you can find one of them. For this equation, if you're given three of these variables, you can find one of them. And what this table does is tells us which variables are not in each equation and helps us be able to figure out how to solve various problems. We're going to do quite a bit of problem solving in class using these equations. You're going to get quite a lot of practice. See you there.